Alright everyone, get on your nerd glasses, because today we are going to talk about making a DIY speaker level to line level converter. I initially thought this video was going to be a 30-second long demonstration because the converter we're making today is literally two resistors that cost less than a cent combined to make. However, the theory behind this is a little important to understand, and I also don't want anybody to damage their equipment, and I want to specifically talk about making this converter for a PA amp like this. That was featured in the last video that I made, where I'm giving away this exact PA amp right here. And this video is going to be split into two parts. One, just like the theory, and then two, the actual construction of making our converter. And I implore you not to jump ahead to just the making of it, because it's really important to understand the theory behind this here. One, because it is super simple, and if you're into DIY audio electronics or you're looking to get into it and you're making this, you should really understand the theory. It's extremely simple, and you should be able to do the math yourself, and you're going to have to do the math yourself when you start to size the resistors for the component that you will be making the converter for. Okay, so I have the situation drawn out on this whiteboard here that we're trying to analyze, where we have the output of our power amplifier and we have a speaker hooked up to it. Now that's normally how these power amplifiers are going to be designed to be ran, right? And the speaker is going to be properly sized for the wattage of your power amplifier. Now, what happens when you want to, instead of connecting the speaker here, you want to connect this to a line level input? Now, since your power amplifier is designed to drive a speaker, which takes relatively a lot of energy to move the diaphragm back and forth of, your power amplifier is going to be putting out a lot more power than a line level input is going to be expecting. So there needs to be some sort of device in between your outputs of your power amplifier and the line level inputs that you're trying to connect to that basically drops the power level coming out of your speaker connections before getting to your input. And the device that we use to do so is called a voltage attenuator. Okay, so I have a really simple circuit diagram drawn here. I have a battery connected to two resistors in series. Now, the total voltage that is being applied by this battery is going to be the sum of the voltage across these two resistors. So the total voltage is going to be the sum of the voltage across resistor 1 and the voltage across resistor 2. Now, moving forward, we need to understand Ohm's law, which says voltage equals the current times the resistance of a component. So let's substitute out the voltage across these resistors. Okay, so the total voltage equals the current times resistor 1 plus the current times resistor 2. Now, since these resistors are wired in a series, the current is going to be the same for through each of these resistors. So let's plug in some mock numbers here to see the voltages across these resistors. Okay, so we have a 10 volt power source. We're going to say this resistor is 9 ohms and this resistor is 1 ohms. So let's do the math here. So when we do the math, we get an amperage of 1 amp flowing through these resistors that are wired in series. And when you do Ohm's law to find the voltage across these, so when you do the math, you get 9 volts across the 9 ohm resistor and 1 volt across the 1 ohm resistor. Now, the beauty of a voltage attenuator is that if you look at the signal across this resistor here, you're going to be getting the same signal that the 10 volt is supplying, except it's going to be reduced by a factor of 10. It's going to be 1 volt signal, right? So you're basically using that to step down the signal to a more manageable level. Now, the 9 volts to 1 volts, depending on what resistor values you use, you could get, different ratios that suit your need. So it's really important to understand the basic concepts of a voltage attenuator. This concept is used throughout audio circuitry everywhere, right? So if you don't understand this, I don't know, go watch another video that explains it better, okay? So as long as we have that underneath our belts, let's move on. Okay, so I've drawn out the situation at hand again. We have the power amplifier here with the outputs. We have the line level inputs over here. In the middle, we have the voltage attenuator that we are going to design right now. And Once again, this voltage attenuator is taking the high power, high voltage signal here, stepping it down to something more manageable that a line level input is used to seeing. The first design parameter we're going to use to size these resistors is figuring out the voltage at our power amplifier, and then our design step down voltage we want to see at the line level input. And the second thing is going to be the impedance of the 3 stages here. Now, I'm really struggling not to get into really excruciating detail about the specifics of the impedance of each stage and the importance of that, and but that's just going to make this video way too long, way too complicated, and I think it's out of the scope of what I'm trying to show here. So we're just going to use a general rule of thumb here, and usually you want your output source impedance to be 1/10 of the impedance of whatever input source you are driving. Once again, I'm not going to get into why, just take my general rule of thumb here. That's usually safe to assume in audio electronics, that, you know, the 10 times impedance rule, I'll call it, okay? So let's start with figuring out the voltage that we are going to be seeing at our power amplifier. In order to get the voltage that we're going to be seeing at our power amplifier, we're going to use this simple equation here. I'm not going to go into how I derived it. Let's just roll with it here. We're going to take the wattage that your power amp is rated for this Bogan amplifier. That is 10 watts, RMS. And we're going to times that by the impedance of our output. For this, I use the 16 ohm output out of the speaker terminals. And let me get out my slide rule to do the math real quick, because this is an analog channel after all. Alright, I'm just kidding. Use the calculator, and you get about 12.6 volts. We're going to round up to 13 volts. So, under normal operating conditions, the speaker terminals on this unit is going to see a max of 13 volts at those the output terminals. Keyword normal operating condition, we're going to talk about a little more about that later when we get into the details about the specific Bogan amp. But for now, let's just worry about this 13 volts at the power amplifier. Now, we need to step down that 13 volts to the voltage that we want to see at our line level input. Now, you could use probably a lot of different values here. In general, generalizing greatly here, line level inputs want to see something around a 1 volt signal. Now, this is going to vary widely depending on your device that you're using. Out of curiosity, I looked at the manual for this mixer, and you know, there are several inputs on this mixer, and they all range from a max of 2 volts to 3 volts, but they want to operate somewhere around 1 volt, right? So that's what we want our design criteria to be. So we want to step down our 13 volt signal to a 1 volt signal here. So this is going to be completely different. The voltage here is going to be completely different depending on the specific situation that you have on hand, right? So you need to do that math yourself to get that voltage here. Now that we have our voltages, we want to figure out what resistance values we're going to use for our voltage attenuator. And we're going to use the simple equation here. We're going to take the voltage that you're seeing at your power amplifier, in this case it's 13, and that is going to equal the resistance of your first resistor over the resistance of your second resistor plus 1. So for this specific situation, there is a ratio of 12 for resistor 1 over resistor 2. Now the specific values you use for this, there's a pretty wide range that you could use, but there's really 2 things you want to think about. One, the current going through the resistors, because whatever resistors you use, you want to make sure it's rated to handle that wattage. And 2 is the impedance matching for each of these 3 stages. And once again, I'm going to try to keep it simple here, but let's go through this design process. If the resistors used here are too low in resistance, you are going to see a lot of current run through them, which is going to cause you to need a resistor rated for a really high wattage. Let's do some quick math here to figure out how much resistance is going to be seen through these resistors. So going back to a formula we've seen before, 13 volts equals the current across resistor 1 plus the current across resistor 2. Remember, in this case, since they're wired in series, the current is going to be the same. And since we know the ratio here, we could plug in for R1. Instead of saying R1 there, we could put 12R2. Okay, so now with this updated equation, we could try out different values for R2 and get a corresponding current that is going through both of these resistors. From there, we could use the power equation to get the wattage that this resistor is going to be dissipating, right? So that equation is going to be P, or wattage, equals the current that we're going to be calculating squared times the resistance value. In this case, R1 is going to be seeing the most power dissipation because it's a higher resistance. So for R here, just do 12 R2 for whatever value we are calculating. And for two reasons, we're going to double this voltage here in order to get the wattage needed for this resistors. We are going to do 26 volts, and whatever voltage you came up with, double it. And the reason for this is twofold. One, just as a factor of safety. Normally in electronics, the factor of safety is only about 25%. But for the second reason, specifically, the last video I did about this Bogan amplifier, I was using this as, I'll call it a color box, right? Where we're pushing the levels extremely hard. And for something we're going to talk about a little later, the voltages I was seeing at the output terminal were actually double of what the amp was rated for, because I was cranking the output of this thing, or the input rather, as much as possible to try to get some distortion in my tests when I was designing this. So for factor safety, we're going to double this, right? Then we're going to get the wattage. Whatever resistors you are using, we want to make sure they're rated for that wattage, right? So a good starting point, especially if you want to try to get away with the 1/4 watt resistors that are just super cheap to get, start with something around 1000K here, right? 1000K in this situation is going to be 1000K ohm resistor here, and something around a 10K ohm resistor here. Once again, you could really vary the ratio here. It's not that important to get it exactly 12 or whatever value you come up with. There's a lot of flexibility here, as long as your resistors are going to be rated for whatever wattage that we're calculating here. You're going to be fine. There's going to be a load of variability here. Don't worry too much about it. As long as you have resistors somewhere around where you need to be, you're going to be fine. The next thing I want you to think about is impedance matching. Once again, I'm really generalizing. I know people are in the comments are going to rip me apart. I'm super generalizing, but we're going to try to stick to the 1 to 10 rule for the impedance matching of, you know, our output source being 1/10 of the impedance of our input source. And I don't know if impedance matching is the best word there, because we're not matching, we're stepping up, but just bear with me here. Now, for the sake of simplicity, in almost all cases, the output impedance of your PA amp or an amplifier in general is going to be really low. For the sake of super simplicity, if you're hooking up to an 8 ohm speaker terminal, just assume your output source is an 8 ohm impedance. If it's 16, just assume 16 ohms. We want to make sure that our total resistance here of these two resistors in series, so your total resistance is going to be R1 plus R2. You want that to be around, at least I should say, 10 times whatever impedance you have here. So if this is a 16 ohm impedance that we're assuming, we want this to be at least 160 ohms. Now, if you're using something like really 100 or 1K ohm resistor, you're going to be way above that threshold and you're going to be fine. Really, your current going through that resistor is going to be more important than this concern here. Now, the impedance of a line level signal, once again, is going to vary widely. Out of curiosity, I checked for this mixer. The various inputs were all rated anywhere from 6K to 10K to even 30K, right? So there's a huge range of variability here. For simplicity, just assume 10K impedance here. And once again, you want to make sure the impedance that your line level signal input is seeing is 10 times more than it's seeing from your voltage attenuator. Now, be careful here though. Your line level input signal is not actually seeing these resistors in series. They're actually seeing them in parallel, and that is because an ideal voltage source is assumed to have 0 impedance. Once again, I'm really generalizing here. I'm trying not to get into specific details, but when you do the calculation there, you're going to want to add these two resistors in parallel, because that is what your line level input is going to be seeing. I'll put the equation for parallel resistance here. If you want to save even more time and just skip the parallel calculation, you could do an approximation here using electronics all the time, where you just assume two resistors in parallel equals the resistance of the lower resistor. So in this case, R2, whatever that resistance is, you want to be a tenth of 10K, basically. So in this case, it's going to be a 1K resistor. Once again, huge range of variability here. Don't get too caught up on it. All right, let's move on. And before I get into the construction here of what I did for this Bogan amp, I want to have two disclaimers here. One, do not do this for a tube amplifier. I repeat, do not do this for a tube amplifier. The impedance matching of a tube amplifier is way more important for the interface, for the output, and whatever the load is on a tube amplifier. The voltages seen in tubes are going to be way beyond voltages seen in a transistor amp. You're talking about thousands and thousands of volts when you're getting really loud peaks with tube amplifiers. So do not do this for tube amp. I can't stress that enough. Please do not. You're going to break something. It ain't worth it. If you're feeling risky, you could always do this. You could always put a shunt resistor in parallel with these two resistors. So for example, if your tube amp is designed to see a 8 ohm load, you could put an 8 ohm resistor like so. And as I stated before, a quick approximation of resistors in parallel, you just assume the resistance of the lower value. So really, your tube amp would be seeing around 8 ohms here. The only caveat here is that whatever wattage your amplifier is rated for, if you have like a twin reverb that's, you know, rated for 135 watts, that resistor should be rated for 135 watts. And that's when things get really expensive, really stupid. You're probably not going to want to do that, right? So just, once again, tube amps, forget it. You ain't doing it. The second thing I want to talk about is possible damage to your amp. Now, things get really tricky here. So if you have an expensive piece of equipment that you don't want to damage, maybe don't take my advice. Maybe don't make this. I don't know. You could buy a device that is manufactured specifically for speaker level to line level, and spoiler alert, they're really just this. For example, the one that's made by, I think it's Russo Sound, it's literally just two resistors. And for their values, they used a 3.9K resistor and a 430K resistor. I'm sorry, just 430 ohms here. So it's basically the same. I mean, it's not basically. It is literally this exact same voltage attenuator. They sell it for 40 bucks. I made mine for less than a cent. But long story short, if you're worried about breaking something, just buy one on the market. Now, we started to get in a gray area with transistor amps, right? Where, you know, your transistor amp is going to be designed to drive an 8 ohm speaker load or a 16 ohm speaker load, and now you're connecting something like a 10K, 20K, 30K resistive load. You know, it wasn't designed to see that type of load. Now, the real question is, are you hurting your amp? Are you going to damage something? And this is such a big question that you're not going to get a straight answer to. I'm not going to give you a straight answer because I don't want you to damage something that's potentially expensive, right? However, if you do this, 99% chance you're not going to damage anything. And the reason I say that is, you know, by doing this, you're essentially operating your transistor amp as if there was no load connected, right? Because no load is the same thing as infinite resistance. And when you're putting something like, you know, a 30K load on a transistor amp that's used to seeing, you know, a 4 ohm load, you know, that 30K load is more close to that, you know, infinite resistance than it is towards the 16 ohms, right? So you're almost driving your amp in a situation that's close to a no-load condition where there's nothing connected to the speaker terminals. Now, if you were to just Google, hey, can I turn on my transistor amp without a load connected or without a speaker connected, you're going to go down a rabbit hole that you won't believe. There is zero consensus on whether or not you could run a transistor amp without a load. Most of the time, and what most people are going to say is, yes, you can run a transistor amp with no load. In all of the transistor amps I've always had, I've ran them with no loads before. It's never been an issue. I've been running this Bogan amp without a speaker load forever. Never had an issue. We're going to talk about the tests I did with this Bogan amp in a second. Haven't had an issue. Usually people say, you know, you're only going to have an issue if you don't have a output transformer in your transistor amp. And spoiler alert, these Bogan amps with the multiple terminal contacts on the end, this video's a mess. In these public address amplifiers, it's really common for them to have output transformers because they'll have multiple settings for the speaker connections, right? Like this one has a 4 ohm, 8 ohm, 16 ohm, a 25 volt, and a 70 volt speaker terminal connections on the back, right? So in order to do that, they need an output transformer. So when people say online, you know, if your transistor amp has an output transformer, you will damage it by not having a load on it, which is basically what we're, you know, doing here. Honestly, the tests I did that we're going to talk about right now, it hasn't been an issue, okay? And really the problem is whenever you introduce an output transformer and you don't have a load connected to said output transformer, you are going to cause a voltage spikes on the primary side of that output transformer. When you ever have a voltage spike, you're potentially, you know, introducing excessive voltages to the components in the system. And last night when I was preparing to make this video, I did some extensive testing on this Bogan amp to make sure what I was saying ain't just bullshit, okay? And I ran this amp in 3 conditions. The first condition with a 4 ohm dummy load on the 4 ohm speaker connection on the back. Then I ran it with no load at all. And then I ran it with my modification that I've made. And I wanted to compare the voltages in the system for each of those scenarios and to see, you know, what the amp was operating at. And for all of these tests, I put the input connection to both of these microphone inputs all the way to 10, and I was blasting a speaker at the microphone, you know, connected to this amp. So I was simulating an extreme distortion, and I learned a couple things when I was doing this. First, that the condition of the no load, where there was nothing connected to speaker terminals, ran almost exactly the same as the condition with my modification installed, you know, with the voltage attenuator installed. The voltages that I was measuring at various components, most importantly the primary voltage of the transformer, the output transformer, they were very similar to the point where we're just going to say they were congruent, right? So I'm correct in saying that whatever your voltage attenuator is designed for, it's going to act as if your transistor has no load. The second thing I learned was the voltages I was seeing internally in the components, most specifically on the primary voltage of the output transformer, was approximately 40% higher in the no load condition than the normal operating 4 ohm speaker load condition. And 40%, you know, that's a pretty significant increase in voltage. And in order for me to determine whether or not this was a problem, I put this thing through some extensive testing. And what I did was, as I said before, both these microphones were cranked to 10. I put both the microphones next to a speaker blasting, so it was an extreme distortion. You know, the inputs were clipping to the maximum extent that this thing was capable of. And I ran this unit for an hour. And this specific unit has a built-in thermostat in the power transformer that if it overheats, it's going to automatically turn off and your output connections will, you know, cease. The output signal, rather. And I ran this thing for an hour in extreme clipping, and I had 0 issues. I had the cover on, so I was making sure it wasn't dissipating heat more than normal. And, you know, this Bogan amp is never going to see an hour of 10 input gain signal on both microphones. You know, that's an extreme condition. You know, in normal recording studio conditions, it's not going to be seeing that, right? So I was putting it through that rigorous test to make sure I wasn't going to damage anything, right? So my conclusions of that test was no issues. The transformer got 5 degrees warmer than it did in normal operating conditions with the 4 ohm speaker connection connected. So 5 degrees is nothing. You know, this thermostat opens up at around 220 degrees Fahrenheit. It was operating at about 135 degrees Fahrenheit. So it still had a lot of temperature room there. No issues. What else? Another thing, I was measuring the voltages at the speaker terminals on the back here, and I was seeing double the voltages than I originally designed for. That's why before, when I told you guys to double the voltage here when you're figuring out the current going through these resistors, that's why I said to double it, because in my test, when I had both of these gain knobs to 10 and I was just screaming into the mic, you know, I was seeing a double the voltage than this unit was rated for. So, you know, those resistors that you want to be using for your attenuator, you know, you want to have some padding in there to be able to handle those big voltage spikes. Okay, so let's take a look at this Bogan amp to show you what I did here. And you could do this in so many ways. This is just specifically how I did it for this amp. Just to quickly summarize, we have the power transformer here. We have the output transformer here. We have the speaker connections here. This is obviously the inside of the amp. You connect normally on the outside, on the back edge here. And, you know, we have all the preamp and all that BS here. Now, all I did was I took the wire, come on, baby. I took the wire that connected to the 16 ohm output here. I unsoldered it, and I put the two resistors, and I have to be a little careful here because this unit's on because my microphone's connected through here. But I'm going to show you how simple my voltage attenuator is. You know what? Actually, let me turn this off. Okay, so here you have the really simple voltage attenuator. The green wire, once again, is the 16 ohm output wire coming from my output transformer. I have that connected to the R1 resistor, which in this case is a 10K ohm resistor. After that, I have a red wire, which eventually goes to my hot signal on the output. And then I have the R2 resistor here, which is a 1K ohm resistor. And as I stated before, when I made this, I didn't do any of the math that I showed earlier in this video to make this. I just took two resistors more or less by chance. I just did a 10-to-1 ratio, and it wound up working out great. That's why I'm saying, you know, the values you use here aren't that crucial. It's more important just to make sure these resistors are rated properly for the wattage that they are going to be seeing, because you don't want them to obviously melt away. Now, across that R2 resistor, you'll see the red wire, which goes to the hot signal on my output, and I have two wires connected to the other side of the resistor, you know, the ground here. One wire goes to the output ground, and the other wire goes to the output, the ground of the Bogan amplifier, just so it's all grounded neatly. Now, in this, you know, demonstration here, I have this just exposed, but I wrapped this in electrical tape. This way, you know, none of the connections can short out anywhere, because you really do not want to short out your output connections. You will damage something in your amplifier. So you want to make sure that this is protected against everything. You know, a really just cheap and dirty way is just to wrap it in electrical tape and tuck it away somewhere safe in your amplifier. You know, this is like a really, you know, DIY crappy way to do it. There's millions of ways you can make this. You can make this externally from your amplifier. You can, you know what, let me turn this back on. All right, we're back. You could do this externally. You could put this in a, you know, guitar stomp box, you know, there's a million ways you could do this. You know, my output here, my red and black wire, I just have it going to the RCA terminal here. And this was actually originally a line in for this machine, but I converted it. I took out the connections here for the line in, and I wound up resoldering that RCA connector for the output of this voltage attenuator. So now that line in is actually acting as a line out, and I just connect it straight to my mixing board right there, and I haven't had a problem since. You hear my voice coming through this microphone right now through this amplifier. So simple. I mean, this costs less than a cent to make. Anyone can do it. You could do it. You know, obviously be careful. You know, don't shock yourself. But yeah, that's it. Let's end this video. I think, once again, I thought this was going to be a minute-long video, and it turned into, you know, like a 30-minute-long video probably. I don't know. We'll see how long we edit it. Hopefully you guys like it. Don't break nothing. Don't do this on an expensive piece of equipment. I don't know. Don't do this on tubes. Blah, I'm leaving. I'm buying. I'm leaving. Wow. That was awkward.
Не ой меня, ей! Не ой меня,